Okay. All right, so to set a little bit of context, modern sort of distributed applications operate by exchanging messages, right? You know, whether it's a web app or a human-to-human messaging app or an IoT app or a phone app or a set of microservices in the cloud, they're all just sending each other messages. And to be secure, private, and trustworthy, our applications must protect these messages from eavesdropping, tampering, and forgery. And these three words are, I think, important for the rest of this talk. Basically, eavesdropping meaning that we don't want other people listening in on information we're exchanging. This may or may not be in the threat model of your application. But tampering usually is, right? If you're doing anything useful with your data, if that data can be tampered by attackers, then your application is no longer really very useful. So tampering usually is in the threat model of an application. And forgery is really a special case of tampering. But basically, if someone can lie about who they are by tampering the incoming messages, then you can be fooled into believing things like maybe, you know, you're a bank and you may give money to the wrong account because someone's forged the sender of a message, right? So eavesdropping, tampering, and forgery, these three things are important for us to have security and privacy and trustworthiness and dependability in our applications. Now, the path that these messages usually take involve many transport layer connections. So even if you think like the simplest applications, like imagine a simple web app where you're loading a web page, we're conditioned to think that, you know, it's simply a client making a TCP connection to a server and then HTTP packets being exchanged on that connection. But in reality, most real websites aren't that simple, right? Because it's client making connection to a load balancer making other connections to some backend making connections to database. There's a whole sort of swath of TCP connections that may be in the path of a application layer message. If we're doing chat over mobile phones, then my phone makes a TCP connection to a server, your phone makes a TCP connection to a server, and our message is exchanged through these two TCP connections at least. But it's very likely if it's a scalable service like iMessage, it may be not just these two TCP connections, but you know there are queuing systems involved and pub subsystems like Kafka or RabbitMQ, and there are several TCP connections going on in the background before in the path of a message going from my phone to your phone. Similarly, if you're doing an IoT system, even if there's a connected switch in my house, the path of an instruction from my phone to that connected switch can involve several transport layer connections and usually does. There's a question in chat about use cases, and I want to get to that later. If I don't get to it in some time, we can come back to it, but give me some time, Carlos, and I will get to it in a bit. All right, so messages. Applications communicate using messages. These messages usually travel over several transport layer connections. So transport layer security protocols like TLS, or if you have Bluetooth security protocol, or if you have LoRaWAN security protocol, or et cetera, all of these transport layer security protocols are unable to provide end-to-end protection against our three threats, eavesdropping, tampering, and forgery, to application layer data, because there are several of those involved, several transport layer connections involved in the path of a message, right? So guarantee of a TLS connection is as long as the length of the underlying TCP connection. And if the message from my phone gets sent to a server over a TCP connection, and then is 2 hours later pulled by your phone from that server, then there's no way TLS can provide an end-to-end guarantee to our messages. The guarantees are broken at that server or any number of intermediaries that we may have in the middle where a new transport connection is created. So the protection of transport layer security protocols are limited by the length and duration of the underlying transport layer connection. So what is Ockam? Ockam is a suite of programming libraries and infrastructure that make it simple for applications to dynamically create end-to-end encrypted, mutually authenticated, granularly authorized, lightweight secure channels that protect your messages end-to-end from their source to their destination. This is especially useful in systems where data is flowing outside of a very tightly controlled data center boundary. And even within data center boundaries, as we scale to large number of microservices and integrations with lots of partners, you may have heard the term zero trust in network boundaries. Basically, the consensus in security circles is that guarding network parameters is very hard and impossible and doesn't scale to the modern use cases of mobile, cloud, IoT, edge, etc. So you need a new type of way of thinking about secure communication, and you need to reason about trust and reliability at the application layer. And Ockham's a toolkit for you to do that at the application layer. So what that means is that you can have secure communication between application layer entities that are not directly connected by simple point-to-point transport connections. En route encrypted messages can travel over multiple transport layer connections and can be stored in message queues, databases, or caches for asynchronous end-to-end protected communication between entities that may not even be online at the same time. So that's the kind of thing you can build with Ockam. This allows us to develop distributed applications that are secure and private by design. So the difference here is that your application layer isn't assuming that the underlying network will somehow provide security and privacy. Your application layer is making active decisions about whether or not it should trust a specific piece of information that it just received, whether it's a connected device receiving a command from a remote server or from a end user, or it's a server receiving data from the physical world, maybe a connected car or something like that. The application layer is making active choices and decisions about whether or not it should trust a particular piece of incoming information. So what does Ockam include? It includes a collection of cryptographic protocols. The first one we will dig into in a fair bit of detail as we dive into some code examples. So the first piece is it has a set of cryptographic protocols that enable end-to-end encrypted, mutually authenticated secure channels. But it also has some other protocols that we will not go into today, but please do check out later. So it has this notion of identity profiles that are isolated by privacy context. So if you're using a cryptographic identity, or think of it like a username, if you use the same username in privacy context one, let's say your manufacturer's interaction. So a connected car talks to its manufacturer, let's say XYZ Motor Company, using identity X. And it also talks to a location data service provider, which provides GPS location using the same identity X. Then the location data service provider and the car manufacturer can combine their data sets to learn more than what was intended for either of those interactions, right? So keeping identity and identity information isolated by privacy context can be very useful in building granularly controlled, least privilege centric applications. And so Ockam includes a set of cryptographic protocols and tools to enable that. It has a set of cryptographic protocols to manage keys at scale. So if you've got, 100,000 connected devices, how do you onboard them? How do you enroll them into your system? This requires all of them generating keys. You need, if you're going to generate keys, you need a mechanism to rotate those keys, revoke those keys, etc. How do you manage all of this at the scale of a fleet? And this is what I've noticed in real world systems is that everyone kind of invents this protocol on their own. Anyone who's faced with this problem, and it's very easy to get those pieces wrong. So in Ockam, we're basically sort of open sourcing a solution to that problem that we're hoping will get improved and matured in the open source ecosystem. Then it includes, Ockam includes protocols for attribute-based access control. Specifically, it has this support for this cryptographic signature scheme called BBS Plus, that allows us to do credentials that have that support selective disclosure. So this is another sort of privacy-centric feature, but essentially, you can imagine that someone can attest 10 attributes about me. Let's imagine like a driver's license is issued to me. The driver's license contains a lot of information about me. And let's say I go to a bar, and to the bouncer at the bar, if I reveal the entire driver's license, then the bouncer learns my address, my date of birth, my name, and a whole bunch of other things. But actually, the only piece of information the bouncer needs to know is whether I'm above 18 or not. And with signature schemes that support selective disclosure, you can present a proof of possession of a signature that proves that I am above 18 without revealing all these other pieces of information about me. So you can imagine that in a connected devices-based system, this can be very useful if the same device is doing access control to machines in a factory, etc. It can limit, again, the mantra here is embracing the principle of least privilege. So it can limit the amount of information that is leaked to people who don't need to know that information. It's built, so Ockam, this core set of protocols are decoupled from the operating environment that they run in. So there are pluggable add-ons for the async runtime, the embedded processor that is running the device, which transport protocols, which cryptographic hardware is available. All of these are pluggable components, and the core of the system is adaptable to the environment. And then we're building these libraries in multiple languages. Rust and Elixir are our primary focus at the moment, but over time, we expect to wrap the Rust library in C, Python, etc. All right, hopefully that answered Carlos's question earlier of like, what does Ockam provide and what are the features? The use case is to build connected systems that embrace this privilege, this least privilege idea, and all communication is end-to-end encrypted, mutually authenticated, etc. All right, so now let's dive into actual code and examples. So to do that, I'm going to take a slightly build from the ground up approach. Actually, to use Ockam, you don't need all of these pieces. But I think to understand what is happening, it's useful to understand them. So we'll do this step by step. So the first idea we need to learn about in Ockam is this term called Ockam node. So an Ockam node is, especially in the Rust parlance, is just an asynchronous execution environment that runs very lightweight concurrent stateful actors called Ockam workers. And these workers, you can route messages from one worker to another worker. And this other worker may be on the same node, or it may be on a node that is several transport connections away. So it may be a remote node. So a node is just any program with Ockam in it, essentially. And what it can do is run these lightweight workers, and it can send messages between these workers. But at this point, someone may ask, well, if it's just an async runtime, what about Tokyo? Or if it's a actor implementation, what about all the other actor implementations in Rust like Actix? Why did Ockam need to have these pieces in the code? So the first thing to clarify there is that we did not re-implement Tokyo, we just use it. But what we wanted was the ability to, with a simple configuration flag, like a feature flag, enable a user to switch the runtime from being Tokyo to being a embedded Ockam node implementation, like the second one here that we have, which is for ARM Cortex M4, for a SAM E54. And you can imagine that over time, there will be several such Ockam node implementations. And having that abstraction over the underlying async runtime allows us to make that switchability really easy, so that our code and your code doesn't need to change just because the operating environment has changed. There's another question in chat about how does Ockam compare to Spire, Spiffy. Ockham's very different from Spire and Spiffy. I think at some point we will write an Ockam add-on to plug into the Kubernetes identity ecosystem, which is what the Spire protocol provides. Okay, so that's one reason to implement Ockam node as an abstraction. Now let's write some code. Okay. So to write some code, I'm going to do this in a library project. So let's generate one, cargo new lib, let's call it Ockam get started. And let's see into this. I'm sure everyone here has at least tried something like this, but what this did is it generated an empty project with a cargo toml and a lib.rs file. I'm doing this in a library because I'm going to write several binary programs next, and an easy way to write lots of binary programs in the same project is to do them as Rust examples. Okay, so let's open this in my editor. And the very first thing we'll do is we'll add Ockam as a dependency. I want to get anything that is above version 0. This will get the latest one. Let's build it so all the dependencies get built. All right. Okay, so now we're going to write our first very simple Ockam node. So let's create an example called 01 node.rs. And what this program is going to do is create a node, create an Ockam node, and shut it down as soon as it starts. All right. So to do that, we're going to need certain Ockam library pieces. So context and result, I think, are the only two things we need for this example. And what we're going to do is write a main function that is annotated with this node attribute. And you can do it without this node attribute, but it's a little bit more verbose. So I'm going to use it here. Async function main. This main receives a mutable context. And it returns a result. All right, so this is our super basic, like almost hello world-ish program. And all it's doing is starting a node. This macro, what it does is it'll start our async executor, which by default is Tokyo, and it'll generate this context and then call this main function that we've provided over here. And so it's basically it avoids a little bit of boilerplate. Let's run this quickly so that we have our basic setup in place. So cargo run. So I printed two tracing messages. It says initializing a node, and then it says shutting down all workers, and then it shuts down. So that was, nothing really happened here. But what's nice about this is that what we're trying to do is all the code from here on out that we will write in this main function, our goal is to keep that unchanged, whether you're running in a super capable Linux machine on a server, or you're running in a tiny embedded node. All you should have to do is change some feature flag in your cargo toml, and everything should stay the same. And that's the reason having this node abstraction is really helpful. All right, so the next thing we're going to do is we're going to create a worker. So what's a worker? A worker is a lightweight concurrent stateful actor. A worker runs on an Ockam node. It has an address that we can specify. It can have some internal state. It can start other workers, and it can send and receive messages to and from other workers. Now, someone might raise the question here is like, if the goal for Ockam is to build these end-to-end encryption and security protocols, what are we doing writing this like actor implementation? And the reason to do that is these cryptographic security communication protocols are stateful protocols, right? And so if we were to expose the management of that state to the users of our protocol, then the API for using the protocol becomes really complex and becomes very easy for someone who's not familiar with the cryptography to shoot themselves in the foot and make mistakes in the management of state, in choosing the right cryptographic primitives, etc. So what a stateful actor provides is that it allows us to hide all of the complexity of the protocol behind a simple function call. And that function call can be run asynchronously in an actor, and all the state becomes can be managed internally. So the reason we needed a worker implementation, because workers enable us to have simple ergonomic APIs for complex multi-step stateful asynchronous communication protocols. And why couldn't we use an existing actor implementation, like maybe Actix, which is popular in the Rust ecosystem, is because Actix it was written pre-async await and is not very decoupled from the underlying async await runtime implementations. And because our goal is to support Ockam workers on lots of different operating environments, it didn't it can't do what we needed to do, and it can't be consistent across all of these operating environments. So we needed to write our own. And the other key thing we needed Ockam workers to do is support this notion of Ockam routing. So that's the reason we needed these workers. So very quickly, let's create a super simple worker. 02. Let's call this. All right, so our workers are going to operate inside a node. So we need all the same boilerplate. Next thing we're going to do is write a worker. Oops, sorry. Okay, so a worker essentially is a type. So we can, let's call this one echoer. And then the next thing we need to do is implement worker for echoer. This implementation needs two associated types. It needs to know which execution context you're running this worker in, which is our node's default context. So we're just going to place that here. The next thing it needs to know is which type of messages does this worker handle. And for our example, echoer, we're going to handle string type messages, but this could be any arbitrary type message that you want to pass around in your system. And we also need this worker macro here. And I'll explain why in just a second, but let's write a function to handle messages. Async func handle message, handle message receives a mutable self reference. It receives a context, which is our execution context. It is also mutable, and it receives the message. And this message is a generic of type routed. I'll explain what this is in just a quick second. And it returns an Ockam result, just like before. Okay, so there's a little bit of boilerplate here, like basically specifying this type and the execution context and which type of messages this worker can handle. We're doing more work to hide this behind this macro, but haven't quite yet been successful. Essentially, we'd like to reduce the amount of boilerplate you have to write to actually write a worker, but currently you have to specify these associated types. But anyway, when we start this worker and start sending it messages, all incoming messages will be received by this function. Let's to start with, let's just print incoming messages. Print. We'll print our own address, and then we'll say we received this message. So we can get our own address from the context and message, all right? And for now, we'll just return OK We don't want to do anything with our message. All right, let's send this worker a message. Let's start this worker and then let's send it a message. So context dot start worker. The first argument here is what is the address you, the application builder, want to give this worker? We're going to call it echoer. And the second argument is what type of worker it is, essentially the type that implements worker, which in our case is echoer. And the next thing we want to do is we want to send this worker a message, context.send. The first argument is who do you want to send the message to, what address? And the second argument is the actual message. So our actual message is going to be a string, hello Ockam dot toString. Okay, let's now quickly make sure we've added everything that needed to be added. Routed worker, that should compile. Let's check. I missed a semicolon. Okay, so ran our example. Dot body. Sorry about that. I am checking what something weird happened. So I'm making sure I didn't make a mistake. Yeah, that's I kept a backup just for making sure I didn't mess something up. Because I want to get to the end and not get stuck in the middle here. I did a little bit of copy paste. I probably messed up like the signature of the function or something. Let's see what happened. All right, so just to kind of quickly talk about the missing pieces. I received a message in my handle. I print the message and then I reply back because the purpose of this worker is to reply back with messages. I basically take the message, take the special field out of it called return route, and the body of the message and send it back. And I'll explain what this is in just a quick second. And then in the main function, I then wait to receive a reply. And when I receive a reply, I print the reply. Not sure where my little typo was in the example, but with that change, it does run. And you notice it starts the node, our echoer worker receives hello Ockam, and then the app receives hello Ockam back, right? And the app here is really my main function. And it gets a default address called app, by the way. Okay, so before I move on, there was a question in chat which was, if an existing application is using Actix or Tokyo, will Ockam integrate easily? I think so. I don't think these ideas should conflict. Definitely not Actix, but Tokyo could be a little bit more complicated. But I think it should work. I haven't done a good solid test of this, but I think it should work. That's a good explanation, Jad. It probably didn't wait for the receive, and that's why it all shut down pretty quickly. That's a good point. Okay, so our super basic example worked. I want to set this context in terms of a quick picture. So this is what we just did. Our main function got an address called app, and our worker has an address called echoer. And what we did is sent a message called hello Ockam and got back a message called hello Ockam. But really what happened is, no, Shambhu, it's not encrypted yet. We're going to turn it into an encrypted message in a couple of examples. So stay with me. But what really happened is the message that went from app to echoer looked like this. It had 3 fields: the payload, which was our actual message, hello Ockam, a field called onward route, which has the address of where this message is going, and a field called return route, which had the address of where this message should be replied to. And similarly, when the message is coming back, this echoer took the return route and made it into the onward route, and set its own return route. So what's really going on under the hood is this type of message is being exchanged. Now I drew this message as a structure, but actually when it's on the wire, this is encoded as a tiny binary protocol, a really compact binary protocol. So the overhead of this information on top of the actual payload is small. All right. And this is like this understanding, this onward route, return route is the key to how we're able to do end-to-end encryption. So as we step through a few more examples, I'll show how this enables general purpose end-to-end encryption rather than end-to-end encryption that is designed only for a specific use case and doesn't work in any other use case. Okay, so let's keep going with our examples. What we're going to do next is this echoer, we're going to reuse this echoer over and over. So let's copy it over to our main library folder, and let's call it echoer.rs. Get this, and we need to export it. So mod echoer pub use colon store. That should do it. And from the worker, we can get rid of this echoer type and instead use our Ockam underscore get started. All right, and just to confirm it still runs, I'm going to run it again. Okay, a couple of quick warnings in worker.rs because we no longer actually use this types. All right, so it all still works, but now we've moved our echoer into a reusable place, and we can keep using it across other examples. All right, the next thing we're going to do is we're going to look at routing in a little bit more detail. So this time around, we'll take our existing code, but we'll define a new type of worker. Just like we wrote an echoer worker, we'll write a new worker. We'll call it hop, hop.rs. And in the interest of saving time, I'm going to copy over the code for this and explain what that does. So all of this boilerplate is the same as our echo example. This is a little bit of like type conversion boilerplate that will go away. The key thing this worker is doing is in these 3 lines. So let's focus on that. What it's doing is it takes the incoming message and it says remove my address from the onward route and insert my address into the return route and then forward the message. So remove my address from the onward route, insert my address into the return route, and then forward the message. This is what this hop worker is doing. Let's go back to our code and let's now start a hop. So we'll give this hop an address h1, and we'll say it's of type hop. And then instead of sending this message directly to a worker address, we'll route it through the h1 worker. So we still wanted to give us an echo back, but we wanted to go to h1 first. Oops, sorry. We wanted to go to h1 first and then go to echoer. And we need this macro, so let's go get it from the library. All right, let's see what happens now. And if it's not making sense yet, I'll show a picture just quick in a second. Oh, forgot to export our hop. All right, so let's see what happened here. The message started at our app. It was received by the h1 worker, our first hop, and then it was sent to the echoer. The echoer then sent it back. It was received by the h1 hop again, and then it was received by our app again, right? So if you think of this in terms of a picture, this is what happened, right? Our message started at the app. It went to h1. It was then forwarded. h1 removed its own address from the onward route and then forwarded over to the echoer. Echoer then replied back and it took the same path back. So in terms of routes, what really happened is something like this. The payload is not important because the payload isn't changed all through this exercise, but onward route, pay attention to what happened. Onward route here was h1 echoer, but when it came out of h1, onward route became just echoer because h1 removed its own address from the onward route and sent it over. Echoer then took the return route, turned that return route into the onward route of the outgoing message, added itself to the return route, and then the same process continued. So we were able to sort of take this journey with this message. But we can go crazy with this type of routing, because what we could do is start any number of these, 2, 3, and you get the idea. We could say, hey, take this route. And now when I run this example, the message takes the route we intended it to take. All right, so now that we understand routing, now let's build a encrypted secure channel. So 04 secure channel. Could someone give me a quick time check? How are we doing? How long do we have before we should end the stream? I think I need about 15 minutes. Brooks? Okay, all right. I'm going to take 15 more minutes. Does that sound okay? Okay, perfect. Thank you. All right, so now we want to do is we want to build a secure channel. And a secure channel is this complicated protocol that involves a bunch of cryptography. And what we're going to do is we want to send this echo message to this echoer worker, but we want to send it through a secure channel. And to do that, the code is very straightforward and simple. Essentially, you create a server, which is, you call it a secure channel listener. You give that server an address. In my case, my address is secure channel listener. And then you create a client. You create a client that talks to that secure channel listener. But before we can do that, we need what's called a vault. And vault is the Ockam abstraction over cryptographic hardware. So if you want to store your keys in secure hardware, like in a secure enclave, like the ones we have in iPhones, or embedded devices these days come with secure elements, or a cloud HSM, etc., you need to write a vault implementation. And currently we have a few of them, but over time we're writing more of them. But anyway, to create a secure channel, you need a place to store these cryptographic keys. And here I'm just creating a software vault implementation. All right, and now once we have this channel, because this channel is based on the workers that we saw earlier, this channel has an address. And because this channel has an address and our send function can route messages through worker addresses, we can say, hey, route this message through this secure channel to the echoer worker. So this message, hello Ockam, is going to start off unencrypted, enter the channel, become encrypted, and then come out unencrypted and reach the echoer worker. So let's run this, and then I'll show a quick picture. Type and alt. And route. Okay. All right, so the secure channel was started, the secure channel initiator was started, the secure channel responder was started, message was passed and delivered to the echoer worker, and a reply was received by the app. In terms of a picture, what really happened is something like this. So secure channel has an initiator, and it has a responder, and it has this phrase called the Authenticated Key Exchange, Our implementation is based on this framework called the Noise Protocol Framework. And actually, we have two implementations of an authenticated key exchange. The other one is based on Signals XGDH. But anyway, either ways, you have this authenticated key exchange that uses public key cryptography and Diffie-Hellman key exchange to arrive at a shared secret between the two communicating parties. And the shared secret never actually travels over the wire, but is mathematically computed by both parties. And once both parties have a shared secret, they can now use symmetric authenticated encryption to guarantee protection against eavesdropping, forgering, and tampering by encrypting the data back and forth to each other. And this is significantly more efficient than public key cryptography. So this is usually the primitive you want. So there's this whole secure channel protocol, but it was entirely hidden to us, the user, and all we had to do is define the listener, just waiting for connections, and define a client that makes and initiates such a secure channel connection. And then what we were able to do is pass messages through this channel. So, okay, so what we just did is we had a message passed through a secure channel. But because we can have any number of hops, why not have a secure channel that goes through several hops? And this is where, because everything is a worker and everything can send messages to each other, the secure channel creation itself can be through a series of hops. So we can get our copied over from our routing example, H1, H2, H3 hops inserted through this, and we run it. Oops, here's your hop. All right, it still worked, and it went through all the various addresses, all the various hops, and it was all encrypted. So I want to talk about transports, but I want to show very quickly. Oh, there's what our slides are. 17. What just happened is the example that we just saw was all of this going on that was hidden from us. So we had a series of hops in the middle. We had this channel initiator. We had a channel listener that was created by that created this channel responder. There was a handshake that happened between. This was our authenticated key exchange that happened between this channel initiator and this channel responder. But to us as the application, all we had to do is call a single function to initiate the secure channel, and then send a message that went encrypted through the series of hops and then was received by the worker. Now, admittedly, we did all of this currently within one Ockam node. And then the one last thing I'm going to show you is how to move this across multiple machines and use this notion of transports. But what we just did is created an end-to-end encrypted secure channel that passed through these several hops, except that was kind of just working inside one machine, which is not very useful. And to all of the complex cryptography was just hidden behind these two simple function calls. Okay, so let's create our final example, and then we can wrap up. Our final example, what we want to do is we want to show that we can route and create secure channels across multiple transport connections between machines. So this example number 5 is going to have a program called Initiator. It'll have another program called Responder. and then a third program, which we're going to call middle. Zero, 5. All right, and so let's start with the responder. And I'm going to, in the interest of time, copy this over, but you're now familiar with this idea. So let's look at what happened here. In this responder, we're creating our echoer. We want to get an echo back from this echoer. We're creating a vault because we need to store our keys. We're creating a secure channel listener. And then we're creating a third thing, which is we're creating this TCP transport that is listening on port 4000. So on this responder program, we've got a echoer worker that's waiting to receive messages to echo back. We've got a secure channel listener that's waiting to receive secure channel handshake requests. And we've got a TCP transport that's waiting for TCP connections on port 4000. Now in our middle program, we're going to do, this one's going to like serve like a TCP layer hop. So we create a TCP transport. We make it connect to the responder, which was listening on port 4000, and we make it listen on port 3000. So this is our little TCP hop, if you will, the second program. And then the first program is actually going to do all the hard work. And so in this first program, what we're doing is we're creating a TCP transport, and we're asking it to connect to port 3000, which is the address of the middle program. And then we're creating a vault because we need it for our secure channel. Then we create our secure channel. But this time in the route, we pass in TCP hops. And we say, hey, go to 3000 or 3000, which in turn will have a way to reach to port 4000. Because this node doesn't know how to connect to port 4000. It only knows how to connect to 3000. And then when you get to 4000, there's going to be a secure channel listener there. So we tell, hey, create a secure channel that goes one TCP hop, two TCP hop, and then to the secure channel listener. And then sending of our echo, sending of our message is exactly the same like our earlier secure channel program. We just say, hey, once this channel is created, send it through the channel to the echoer. And the message just magically enters the channel, gets encrypted, gets decrypted, and appears on the other side and is received by the echoer, and then a reply is sent back. So we've got these three programs. Let's see if it works. So I need to split my screen. And all right, so over here, I'm going to run my responder. And here I will run the middle program. And then over here, I will run, we can ignore the warning. Here I will run the Initiator program. I misspelled the Initiator, sorry about that. Okay, so what just happened? Our responder did receive an echo. The echoer did receive a message. It came through this middle node and it started here, and I can keep repeating this. I can do this again and again and again and again. And what we're doing, what's happening is the message starts at this node, the initiator goes to the middle node, is forwarded to the responder. gets decrypted here, an echo is created, gets re-encrypted, goes back to the middle, comes back to the initiator. So to conclude, what this means is that we're able to use this paradigm. And like in typical, even though we went through several steps to create this, a typical application only needs to write these 20 lines of code or 25 lines of code to create end-to-end secure channels with something that is remote. And what's cool is that even though this was TCP and secure channel listener, it can be Bluetooth with some Bluetooth address, TCP and secure channel listener. It can be Bluetooth, UDP, TCP. You can get all sorts of creative with the path across which these end-to-end encrypted secure channels are created. Someone had a question in chat about, well, this sounds similar to messaging systems like Kafka and RabbitMQ and other things. It is, except Kafka and RabbitMQ, etc., don't have end-to-end encryption as a first-class primitive. In fact, we have built a integration with Kafka, so you can have end-to-end communication through Kafka. And if you're interested in learning more about that, check out the last Ockam open source community call video. Our team member Daniel goes into quite a bit of detail about how that works. But essentially, you could imagine that a device in my house could have an end-to-end encrypted communication with my phone when I'm away on a vacation through a service in the cloud that is using Kafka for storage. And both of us are not even online. When I'm on a plane, my phone is offline, but I still receive end-to-end encrypted messages from the devices in my house, like my connected doorbell or a light switch or something like that, or a machine in a factory. All right, to conclude then, what we just saw was a picture that looked like this, where we had messages go over through from an initiator to a middle to a responder. We already saw how all of the internal cryptographic protocol detail is hidden. And this only scratched the surface of what's in Ockam. We essentially just talked about this first piece. There's a work we're doing around all of these other pieces. Please check out the project. It's all being actively developed, and we are eager to collaborate, whether it's adapting it to your use case or environment, or if you want to do contributions, feel free to look at some of our help wanted bug issues. And thank you all for listening. You can find Ockam at that repo and me on Twitter at that address. Thanks a lot. Yeah, I apologize for this. Live coding always ends up being slower than you expect it to be. So I went way over time. Thanks for everyone who stuck around.
That is absolutely okay. We have some questions in Twitch chat. So one question is, what is the encryption algorithm?
So the actual, after the secure channel is established, the actual encryption algorithm is AE80 AES 256, which is authenticated encryption with associated data using AES 256-bit cipher. But that question is incredibly nuanced because actually to establish the secure channel, we use a certain handshake protocol, which is essentially the philosophy of the project has been we want to take proven primitives and make them easy to use. We're not trying to invent cryptography. So we're taking ideas that have been proven in projects like Signal and other end-to-end encryption projects. So our handshake is basically directly inspired from the Signal project.
In the last example, was the middle executor able to decrypt the message, or could you set it up so the middle executor could not even decrypt the messages that it was passing on behalf of other endpoints?
Yeah, so the middle one basically only saw encrypted data and couldn't decrypt it, but it saw routing information. So it saw that a message is going from initiator to responder. But actually, because the channel protocol is so lightweight, essentially the overhead is around like 16, 17 bytes to create an encrypted channel. You can tunnel a channel inside a channel. And because we already have this routing idea, essentially, if you want to hide routing information along a certain path, you take a channel and you tunnel it through another channel, which is kind of like Thor's onion routing idea. But you can create privacy preserving paths where even routing metadata is not revealed with the same toolkit, with just a rearrangement of how you make the secure channel setup.
And is the routing metadata extensible? Can you make your own metadata fields that are used for your own like application specific routing?
Not at the moment. Basically, we see that routing message surface as the surface that ties all Ockam nodes together. Basically, all Ockam nodes are free to do whatever they want. Like an Elixir implementation can be a completely different concurrent worker implementation from a Rust implementation. A C implementation can be completely different. The only thing tying them together is the routing protocol. And so we see that as that surface is important to us and we want to keep it small. But this idea of like passing metadata around has come up, and what we might do is define a additional metadata protocol on top of the routing protocol, which is maybe not supported by certain nodes. And that's how we might actually propose it. If you're interested in that, feel free to like file an issue and describe a use case, and I would love to chat more about it.
Thanks.
Mrinal, I have a question. Like right now, that hopping route, right? It looks like a user has to predefine like before sending the message. Is there any possibility like automatic routing?
Yes, exactly. Very much so. We haven't done work on this yet, but essentially discovery of a route can happen at the originator, or it can happen along the path, right? So it could be that an endpoint device is given some configuration, which is very common in IoT scenarios, right? Like a device that is installed in my house always takes the first hop to a gateway and then second hop to a cloud service. That path is defined and it's very unlikely to change. So for that device to be configured with this route is fairly straightforward. But that's not always the case in all use cases. So in cases where a hard-coded route is not ideal, what we want to do is describe a discovery protocol where, given the identifier of a destination, you can query some central place to say, hey, give me the route and current public key of that destination so that I can establish a secure channel with that destination. That discovery protocol is mostly in like sketch stages at the moment, but we want to support it. And the other nuance in that question is that because the routing information is not by default protected by the secure channel, nodes in the path of the route can augment it. So this is incredibly powerful. So for instance, let's say I have a device in my house that is behind a NAT, and I want things in the external world to reach this device in my house. So we have a service we're developing called Ockam Hub, where this device in my house that is behind a NAT makes a connection to the service and says, hey, give me an address over at your location that I can share with other people. And this device in my house sets up a secure channel with that hub. And then it shares with other external things. Hey, if you want to send me a message, send it to Ockam Hub address 1234. And messages come over there, and they're augmented with this internal routing information that is not visible to the world and delivered to me. So because routes are not protected by the secure channel, we can do all sorts of manipulation of this kind to create lots of topologies, but protect them with secure channels because we can then wrap a secure channel along this path and a different secure channel along this path and an end-to-end secure channel through the two secure channels. And because this is also lightweight and like Lego-like, you can do all that.
Thank you.
There's a chat question. It doesn't sound like Ockam has any durable component to messaging. Yes, we do. There is a proposal called Ockam Streams. Please have a look. It is very much in the works. But essentially what we want to do is have a super lightweight durability definition, and we want to rely on underlying existing systems. So like if we can use Kafka in an environment, we'd much rather delegate to Kafka and just have our very thin protocol on top. The Ockam Streams proposal is work in that direction. It's fairly detailed. Please check it out, and we'd love feedback. Also from Twitch, H1, H2, even though they were part of the communication chain for the handshake, are unable to figure out what their shared secret was due to properties. Precisely, yes. H1, H2, H3, like all these hops in the middle are just exposed to the routing information. They cannot do anything to tamper the actual application data. But what they could do is not forward the message at all. Right, that's a problem you could have from a H1 or a hop in the middle. And that's where you basically need an SLA from a routing provider, right? And so if someone is being a Ockam router, then that's a SLA that provider is providing. So there's trade-offs there in terms of like what types of things we could mitigate.
Can you do like a select for various hops where it could go through 1, 2, or 3, whichever one happens to get it first?
Yes. So this is totally up to the thing that is in the path, right? Because the things in the middle can behave, can manipulate routing information freely. You can easily write a hop worker that is selective, and you can then put in a priority notion into that hop worker, which is if I'm unable to resolve this path, I'll resolve this path. But what's important here is that this is not network layer routing, right? So it's fairly reliable endpoints, right? Because you're basically routing from web service to web service or IoT gateway to IoT gateway. They're fairly reliable endpoints, and they're not like, you're not switching networks all the time. It's different in that sense, but you could do it if you wanted to. Thanks a lot. I really, really enjoyed it. Thanks everyone for the questions. And please do check out the project on GitHub. Our discussion forum is also on GitHub. So we use GitHub discussions. If you have questions, thoughts, ideas, we'd love to hear.
Awesome. That's great. Well, I declare that another successful Rust meetup talk here. I hope that you all have a great rest of your night, and we'll see you online next time.
Thank you.
Thank you.
Bye, everyone.
Bye. Bye.